Right now, 4 astronauts are hurtling through deep space, farther from Earth than any human has been in over 50 years. And in a few days, everything comes down to one moment: re-entry. The most dangerous 5 minutes of the entire mission. The moment when a heat shield, the same heat shield that came back cracked and broken the last time NASA used it, is the only thing standing between 4 people and temperatures that would vaporize them instantly. Before this mission launched, engineers went public with their concerns. Former astronauts compared what they were seeing to the decisions made before Challenger, before Columbia, and NASA launched anyway. This is the story of the gamble NASA made and why the most critical test of Artemis II hasn't happened yet. Part 1. The Pacific Ocean off the coast of Baja California is typically unforgiving, but on the morning of December 11, 2022, the waters were quiet enough to recover a falling star. Waiting in those waters was the USS Portland, a US Navy amphibious transport dockship equipped with a floodable well deck. The crew, alongside a joint Navy-NASA recovery team, was scanning the sky for the culmination of a 1.4 million dial journey. They were waiting for Artemis I. At 12:40 p.m. Eastern Time, a 9-ton Orion capsule descended gracefully under 3 massive red and white parachutes. It hit the water at a sedate 18 miles per hour. Mission control erupted. The Artemis program, humanity's triumphant, long-awaited return to lunar exploration, had completed its first uncrewed test flight. NASA Administrator Bill Nelson lauded the mission as a historic victory. In front of the cameras, the narrative was one of flawless execution, but engineering truth is rarely found in press conferences. It is found in the physical inspection of the hardware. Here is why this matters. The top priority of the Artemis I mission was never the launch. It was the return. As mission manager Mike Sarafin noted before the flight, there is no wind tunnel, no arc jet, and no aerothermal testing facility anywhere on Earth capable of replicating the hypersonic re-entry of a 16.5-foot-wide heat shield at Mach 32. You cannot simulate the physics of returning from the moon. You have to actually fly it, burn it, and see what the vehicle confesses when it gets back. When the recovery team secured the blackened capsule and pulled it into the flooded well deck of the USS Portland, the water drained away, leaving the spacecraft sitting on a protective cradle. Engineers approached the underside of the vehicle. They were expecting to see a smooth, uniformly charred surface. The heat shield is made of a proprietary material called Avcoat, an ablative resin hand-injected into more than 330,000 individual fiberglass honeycomb cells. The fundamental principle of an ablative shield is elegant destruction. It is designed to burn. As the spacecraft hits the atmosphere, the friction generates temperatures approaching 5,000 degrees Fahrenheit, roughly half the temperature of the surface of the Sun. The Avcoat is supposed to slowly and predictably melt away, absorbing the thermal energy and carrying it away from the spacecraft. Think of it like a block of dry ice on a hot skillet. As the ice sublimates into gas, it creates a protective, cooling boundary layer that pushes the intense heat outward. The mechanism relies entirely on uniformity. It requires the material to recede smoothly, layer by microscopic layer, but when inspectors looked at the Artemis I heat shield, they did not find a smooth, uniformly ablated surface. They found a cratered landscape. There were over 100 distinct locations where the Avcoat had not melted. It had fractured. It had chipped. It had violently popped off in thick, jagged pieces. In some areas, the pitting was alarmingly deep, exposing a chaotic topography of missing material. 4 separation bolts embedded in the shield had partially melted through their thermal barriers, leaving severe gouges instead of a predictable char pattern. Stay with me for a moment. Let that sink in. Material did not just burn away. Solid chunks of the spacecraft's primary defense system physically liberated from the vehicle while traveling through the atmosphere at hypersonic velocities. Not metaphorically, not as a headline exaggeration, something physical broke off in flight. The mathematical models built by the smartest thermal engineers on the planet completely failed to predict this behavior. Now, intellectual honesty demands we state a critical fact. The capsule survived. The interior crew cabin remained perfectly intact and unaffected. The mannequins strapped inside, Commander Munikin, Campos, Helga, and Zohar, recorded no fatal data. If human beings had been on board Artemis I, they would have walked out of the spacecraft alive. But in the unforgiving discipline of aerospace engineering, unexpected survival is not the same thing as safety. A catastrophic failure mechanism that miraculously stops just short of breaching the hull is still a catastrophic failure mechanism. It is a warning. NASA was now staring at a deeply sobering reality. The most critical piece of safety hardware on the Orion spacecraft possessed a structural flaw they did not understand, and the very next mission, Artemis II, was scheduled to put 4 human beings into that exact same vehicle. Part 2. The physics of the wall. At 400,000 feet above the surface of the Earth, the vacuum of space begins to give way to the exosphere. This boundary is invisible, silent, and physically absolute. When the Orion spacecraft crossed this threshold on its return from the Moon, it was traveling at 24,500 miles per hour. That is Mach 32. It was moving at nearly 7 miles every single second. This is not a landing. This is a controlled collision. To understand the sheer severity of the damage inflicted on the Artemis I heat shield, we first must understand the environment it was subjected to. Returning from low Earth orbit, the domain of the International Space Station, requires a vehicle to bleed off speeds of roughly 17,500 miles per hour. Returning from lunar distances is a fundamentally different mathematical problem. The kinetic energy a spacecraft possesses scales with the square of its velocity. That means a lunar return vehicle does not just face slightly more energy than a low Earth orbit vehicle, it faces an exponential structural nightmare. Let's be precise about what this means. The popular misconception is that re-entry heat is caused by the friction of air scraping against the hull of the spacecraft. That is structurally false. If friction were the primary heating mechanism, the vehicle would vaporize before it reached the stratosphere. The heat is caused by atmospheric compression. Think of it like this. When you push the plunger down on a manual bicycle pump, the base of the pump gets warm. You are physically compressing the air molecules into a smaller volume, and that rapid compression generates thermal energy. Now, scale that mechanism up to a 9-ton capsule slamming into the atmosphere at 32 times the speed of sound. The air molecules directly in front of the Orion spacecraft cannot get out of the way fast enough. They pile up, brutally impacting one another, compressing into a super-dense, hyperheated layer of gas. This is known as a bow shock. It is a physical wall of plasma. Within seconds of hitting the denser layers of the atmosphere, the temperature at the stagnation point, the dead center of the heat shield taking the brunt of the atmospheric resistance, spikes to 5,000 degrees Fahrenheit. That is roughly half the temperature of the surface of our Sun. The air literally tears itself apart, ionizing into a glowing envelope of plasma that physically blocks all radio communications. The spacecraft is encased in a man-made star. Stay with me for a moment. Let that land. The vehicle is trapped inside a 5,000-degree plasma sheath, hurtling blind through the upper atmosphere. The only physical object preventing the immediate incineration of the aluminum and titanium crew cabin is a specialized layer of composite resin less than 3 inches thick. That resin is the Avcoat heat shield. It does not just experience heat, it absorbs pressure, it absorbs acoustic shock waves, and it absorbs an unrelenting barrage of ionizing radiation. The engineering solution to surviving this environment was born in 1951. An aerodynamicist at the National Advisory Committee for Aeronautics named H. Julian Allen realized that if you built a spacecraft shaped like a needle, it would cut through the air efficiently, but the concentrated heat at the tip would melt any known material. Allen proposed a deeply counterintuitive solution, blunt body theory. Instead of piercing the atmosphere, a spacecraft should punch it. By making the bottom of the capsule wide, flat, and aggressively blunt, the vehicle intentionally creates a massive, detached bow shock wave slightly ahead of the physical heat shield. This invisible wall of compressed air does something miraculous. It forces 90% of the generated thermal energy to flow around the spacecraft and dissipate into the atmosphere, rather than soaking into the vehicle itself. The blunt body shape is what keeps the capsule alive. The remaining 10% of the heat, the 5,000 degrees that does reach the hull, is what the Avcoat ablative shield is built to manage. The system relies on absolute predictability. The mathematical models dictate that the immense pressure and heat will remain evenly distributed across the blunt face of the shield. The geometry of the capsule, the density of the air, and the specific chemical composition of the heat shield form a delicate, interconnected physics equation. If any single variable in that equation deviates, the boundary layer collapses. During Artemis I, the blunt body physics worked, the bow shock formed, the temperatures spiked exactly as modeled, The vehicle bled off its immense orbital velocity. It is precise, it is violent. It is an act of sheer physical trauma. But when the plasma faded and the capsule drifted down to the Pacific, the physical evidence revealed a terrifying truth. The laws of fluid dynamics had functioned perfectly, but the material science of the shield had fundamentally betrayed them. The Avcoat had not behaved like the trusted legacy material NASA assumed it was. Part 3. The Apollo Illusion. When NASA was tasked with building the Orion spacecraft, they did not start from scratch with the thermal protection system. They reached back into the history books. They selected Avcoat, the exact same ablative material that successfully brought the Apollo astronauts home from the moon half a century ago. It was a brilliant public relations narrative. It suggested unbroken heritage, tested reliability, and guaranteed safety. But the Avcoat on Artemis, I was not the Avcoat that flew on Apollo. Here is why this matters. The catastrophic failure of the Artemis I heat shield was not a failure of the baseline chemical resin itself. It was a profound, unpredicted failure of architecture. To understand the difference, we must look at how the Apollo heat shield was physically constructed. In the 1960s, engineers understood that the extreme thermal and mechanical stresses of re-entry would naturally cause the Avcoat resin to crack. To prevent those cracks from spreading and destroying the entire shield, they designed a monolithic fiberglass honeycomb matrix containing roughly 330,000 individual hexagonal cells. Technicians armed with specialized caulking guns hand-injected the paste-like Avcoat resin into every single one of those 330,000 cells. It was an agonizing, labor-intensive process that took more than 6 months to complete for a single vehicle, but it worked. The honeycomb cell walls acted as natural physical barriers, crack arresters. If the material in one cell fractured, the damage stopped at the fiberglass wall. Furthermore, this honeycomb matrix naturally breathed. It possessed a critical mechanical property called permeability. As the extreme heat baked the resin, the resulting gases could safely vent outward through the matrix and into the slipstream. NASA actually used this exact same exhaustive hand-injected honeycomb method for Orion's first brief low Earth orbit test flight in 2014, known as EFT-1. But as the Artemis program spooled up for lunar return, schedule and budget pressures mounted. The 6-month, hand-injected honeycomb manufacturing process was deemed too slow, too expensive, and prone to internal strength inconsistencies at the seams. So, NASA fundamentally altered the blueprint. For Artemis I, they eliminated the 330,000 cell fiberglass honeycomb matrix entirely. Instead, they manufactured the Avcoat into just under 200 solid pre-machined blocks. These heavy blocks were glued directly onto the underlying carbon fiber skin of the heat shield, like a massive, three-dimensional jigsaw puzzle. Let's be precise about what this means. They removed the structural skeleton that was actively preventing the material from cracking, and they removed the microscopic pathways that allowed the material to breathe. Furthermore, environmental regulations enacted since the 1970s meant the specific chemical additives used in the original Apollo resin were no longer legally compliant or commercially available. The modern Avcoat had to be subtly reformulated. They changed the chemistry. They changed the physical structure. They changed the manufacturing process. Yet, it was still marketed as the trusted legacy Apollo material. When the solid Avcoat blocks on Artemis, I was subjected to the violent 5,000-degree thermal shock of lunar re-entry. The resin began to bake and off-gas exactly as it was supposed to. But without the permeable honeycomb structure to let those expanding gases escape, the pressure inside the solid blocks had nowhere to go. Think of it like heating a sealed, rigid can of soup on a stovetop. The pressure inside aggressively builds, fighting against the structural limits of the container until the material violently yields. The Artemis I heat shield did not melt away smoothly because it was physically suffocating. The trapped gases aggressively expanded inside the solid blocks, physically blowing thick, jagged chunks of Avcoat completely off the spacecraft in a process engineers call spallation. Stay with me for a moment. Let that land. The agency took a proven, life-saving legacy system, stripped out the critical physical architecture that made it safe in order to expedite manufacturing, and then watched as the modified system literally blew itself apart in the upper atmosphere. Part 4. The Mach 32 skip. To understand a failure of hardware, you must first understand the violence of the flight path. The Apollo capsules returned from the moon on a direct ballistic trajectory. They hit the atmosphere like artillery shells, riding a single brutal wave of deceleration straight down to the ocean. It was an incredibly punishing profile, subjecting the astronauts to immense gravitational forces. Artemis I did not fly a ballistic line. It flew a wave. For the first time in the history of human-rated lunar spacecraft, NASA executed a maneuver known as a skip re-entry. A skip re-entry is a masterpiece of orbital mechanics designed to solve two critical problems: gravitational load and landing precision. When the Orion capsule hit the upper atmosphere at 24,500 miles per hour, it did not continue straight down. It plunged to an altitude of roughly 200,000 feet, bleeding off a massive amount of speed in a sudden surge of plasma and friction. Then the spacecraft commanded its thrusters to fire, physically rolling the asymmetrical capsule to change its center of gravity. It used aerodynamic lift to bounce. The capsule skipped off the thickening atmosphere, ascending back up toward the vacuum of space, reaching an altitude of nearly 300,000 feet. It glided through the thinner air, cooling down, flying thousands of miles across the globe, before finally pivoting and making its second final plunge to the Pacific Ocean. Think of it like skipping a stone across a quiet pond. Now, imagine the stone weighs 9 tons. The pond is a wall of compressed atmosphere, and the friction generates temperatures hotter than a blast furnace. The maneuver is mathematically brilliant. It divides the re-entry into two distinct phases. It lowers the peak G-forces, preserving the physical health of the human crew. It extends the glide range, allowing the capsule to precisely target a recovery ship anywhere on Earth. It is a necessary structural evolution in spaceflight. But it completely changed the thermodynamic reality of the heat shield. By executing a skip re-entry, Artemis I subjected the newly redesigned non-permeable Avcoat blocks to a dual-pulse thermal profile. The hardware was forced to endure a catastrophic spike in temperature, a brief period of atmospheric relief, and then a second catastrophic spike. Let's be precise about what this means for the chemistry of the shield. During the first plunge, the outer surface of the Avcoat instantly charred. The intense heat began to radiate inward, penetrating the 3-inch thickness of the solid blocks. But heat transfer takes time. When the capsule skipped back up into the freezing upper atmosphere, the outer surface of the shield rapidly cooled. The interior of the blocks, however, did not. The thermal energy was trapped inside the material. Engineers call this a heat soak. While the capsule glided in the freezing exosphere, the internal temperature of the Avcoat was steadily rising. The chemical resins deep inside the blocks were baking. They were converting into gas. And because NASA had removed the breathable honeycomb structure used in Apollo, that expanding gas was imprisoned inside a rigid, hardening shell. The pressure grew entirely unchecked. Then came the second plunge. The Orion capsule fell back into the dense atmosphere, violently reigniting the bow shock. A second wave of 5,000-degree plasma hammered into the shield. The sudden, extreme thermal shock hit a material that was already internally pressurized, deeply heat-soaked, and structurally compromised. The trapped gases violently expanded past the tensile strength of the Avcoat box. The material detonated. Thick, solid chunks of the primary thermal protection system fractured and blew off into the slipstream. The ablative process, designed to be a smooth, elegant dissipation of energy, devolved into uncontrolled physical fragmentation. The orbital mechanics functioned with absolute perfection. The material science buckled entirely. Stay with me for a moment. Let that land. The smartest engineers on the planet built a flight profile to protect the soft tissue of the human body, but in doing so, they created a thermal environment that actively tore apart the very armor keeping them alive. Part 5. The Hangar Revelation. The immediate aftermath of a spacecraft recovery is an exercise in managed chaos. There is salt water, recovery divers, and the pitching deck of an amphibious transport ship. But definitive engineering analysis cannot be conducted on the ocean. It requires stability. It requires a sterile environment. Weeks after splashdown, the Orion capsule was transported across the country to the Operations and Checkout Building at the Kennedy Space Center in Florida. Inside this massive climate-controlled cleanroom, technicians began the methodical process of dismantling the spacecraft. They unbolted the 16.5-foot diameter heat shield from the base of the crew module. They hoisted the heavy blackened dish into the air. secured it to a massive industrial turnover stand, and slowly rotated it vertically so the primary face was fully exposed to the inspection team. This was the moment of truth. They expected a continuous, uniform layer of aerodynamic jar. They expected a seamless, predictable topography. They expected absolute mathematical validation. What they got was a crime scene. The NASA Office of Inspector General would later release a blistering formal report cataloging the exact extent of the damage. But the engineers standing under the fluorescent lights of the hangar saw the reality first. There were more than 100 distinct locations across the surface of the shield where the Avcoat had completely fractured. The ablator had not melted. It had snapped off. It left deep, erratic gouges in the armor. Let that sink in for a second. A spacecraft designed to carry 4 human beings had just survived a Mach 32 re-entry by leaving a physical trail of its own primary defense system scattered across the upper atmosphere. Here is why this matters. The damage was not merely superficial pitting. It was actively threatening the structural hardpoints of the vehicle. Scattered across the heat shield are critical separation bolts, the physical explosive mechanisms required to jettison the shield before splashdown so the parachutes can deploy properly. These bolts are deeply recessed and protected by their own localized thermal barriers. But because the surrounding Avcoat violently spalled off in heavy chunks, those protective barriers were suddenly exposed. The 5,000 plasma of re-entry found these newly created topographical valleys. It flowed aggressively into the craters. It reached the hardware. Inspectors found that several of these critical separation bolts had partially melted and severely eroded during flight. Think of it like an armored vest. If a ceramic plate stops a rifle round but shatters predictably in the process, the wearer survives. But if the plate shatters in 100 unpredicted places and physically exposes the fragile seams holding the vest together, the armor has structurally failed, even if the wearer miraculously walks away from that specific firefight. The Artemis I heat shield survived the descent, but it demonstrated an unprecedented mechanism of failure that could not be predicted, controlled, or mitigated by any existing mathematical thermal model. The math lied. The engineers in the hangar realized immediately that the baseline assumption of how this modern, solid-block Avcoat behaved in a dual-pulse lunar thermal environment was fundamentally, physically incorrect. They were no longer looking at a wildly successful test flight. They were staring at a catastrophic hardware anomaly. Part 6. The Mechanics of Ablation. To understand why the heat shield failed, you must first understand how it was supposed to survive. At Mach 32, fire cannot be repelled. It must be managed. When aerospace engineers talk about a heat shield burning away, they are not describing a simple bonfire. They are describing a highly choreographed endothermic chemical reaction known as ablation. This is not the physics of melting. This is the physics of pyrolysis. Here is why this matters. The Avcoat material is essentially a matrix of epoxy novolac resin infused with microscopic silica glass fibers. When the 5,000 plasma of the bow shock hits the outer surface of the shield, the heat violently forces the chemical bonds of the resin to break apart. This decomposition, pyrolysis, absorbs a massive amount of thermal energy in the process, but the heat does not destroy the material completely. It transforms it. As the resin vaporizes into a mixture of carbon and hydrocarbon gases, it leaves behind a porous, blackened, carbonaceous skeleton called the char layer. This char layer is intensely critical. It is a terrible conductor of heat, meaning it physically insulates the virgin Avcoat beneath it. Furthermore, as the char layer glows incandescently white-hot, it acts as a thermal mirror, actively radiating up to 75% of the incoming heat back out into the freezing vacuum of the atmosphere. It is brilliant. It is elegant. It requires absolute chemical precision. Let's be precise about what this means for the gases trapped inside. The hydrocarbon gases generated by the pyrolysis reaction deep inside the shield must aggressively expand. In a properly functioning ablative system, these gases migrate outward, flowing through the microscopic pores of the carbon char layer. As they pass through, they literally cool the glowing char from the inside out. When these gases finally reach the surface of the spacecraft, they are aggressively injected directly into the 5,000 plasma shockwave pressing against the hull. Engineers call this mechanism blowing. Think of it exactly like human sweat. When your body overheats, It pushes liquid through the pores of your skin to evaporate, creating a microscopic cooling boundary that carries heat away from your tissue. A spacecraft does the exact same thing, but instead of water, it sweats superheated hydrocarbon gas. This outward blowing pressure forcefully thickens the boundary layer of the atmosphere, physically pushing the flesh-incinerating plasma further away from the spacecraft's skin. Only after all of this, the pyrolysis, the outgassing, the convective cooling and the blowing, does the outer surface of the char layer finally react with the oxygen in the atmosphere and slowly, predictably erode away. That erosion is called recession. It is designed to shed material at a microscopic, meticulously calculated rate. The mechanism is not merely resisting the plasma, it is actively using the plasma's own thermal energy to fuel a chemical force field. Stay with me for a moment. Let that land. The entire mathematical foundation of human survival during re-entry rests on a single, non-negotiable physical requirement. The superheated pyrolysis gases generated inside the heat shield must be able to escape freely through the surface. If the gas cannot vent, the boundary layer collapses. If the gas cannot vent, the char layer is not cooled. If the gas cannot vent, the energy has nowhere to go. And on Artemis I, NASA had replaced the breathable, hand-injected Apollo honeycomb with dense, solid blocks of unyielding resin. The gas could not escape. Part 7. The trapped gas anomaly. The most dangerous environment for a modern spacecraft is not a catastrophic spike in thermal energy. It is a temporary, deceptive lack of it. It was not the fire that broke the Artemis I heat shield. It was the cooling. For nearly 2 years, NASA engineers subjected samples of the modified Avcoat blocks to aggressive, high-fidelity testing inside the arc jet facilities at the Ames Research Center in California. They were hunting for the exact mechanism that caused the solid armor to violently splinter. When they finally forced the material to confess its physical weakness, the answer completely inverted decades of aerospace logic. Here is why this matters. Before Artemis I launched, the heat shield had been mathematically modeled and physically tested against the absolute maximum heating rates imaginable. When you subject this solid Avcoat to a sudden, overwhelmingly severe thermal environment, it performs brilliantly. The intense, localized heat instantly flashbakes the outer surface, aggressively generating the porous char layer we discussed earlier. The gases immediately vent through the newly formed pores. The pressure escapes, the shield survives. But Artemis I did not experience a single, overwhelming thermal event. It flew a skip trajectory. When the engineers at Ames replicated the exact, lower-intensity thermal profile of the skip, specifically the gliding phase in the exosphere between the two atmospheric plunges, they unlocked a terrifying physical truth. During that high-altitude glide, the external heating rates drastically dropped. The surface of the spacecraft was no longer being flash-baked by plasma. But deep inside the 3-inch thickness of the Avcoat block, the thermal energy from the first plunge was still intensely radiating inward. The chemical resins deep within the material were silently cooking. They were decomposing into expanding hydrocarbon gas. But because the external heating was not severe enough during this glide phase, the outer surface of the Avcoat had not yet transformed into a fully porous char layer. It remained dense, it remained rigid, it remained physically sealed. Let's be precise about what this means. The very maneuver designed to save the crew by lowering the total heat load actually slowed down the critical chemical transformation of the shield. It created a pressure cooker. The expanding gases deep inside the block began pushing violently against an unyielding, uncharred outer shell. The material possessed zero permeability. The pressure compounded exponentially, fighting against the tensile strength of the solid resin. When the capsule plummeted back down for its second violent collision with the atmosphere, the sudden secondary shockwave of heat and acoustic vibration was the final trigger. The internal pressure fundamentally overwhelmed the structural integrity of the blocks. The material did not melt. It detonated from the inside out. Think of it like an explosive decompression in a deep-sea submarine, operating in reverse. A solid mass, silently accumulating immense internal pressure, instantly shivering into fragments when it can no longer contain the physical force pushing outward. The arc jet testing yielded one final devastating piece of evidence. Prior to the launch of Artemis I, engineers had actually identified a few isolated patches of the Avcoat on the vehicle that were naturally slightly more permeable than the rest. When inspectors examined those specific patches after the flight, They found zero char loss. They found zero cracking. The gas in those isolated locations had vented safely, exactly as it was supposed to. Stay with me for a moment. Let that land. The engineers possessed physical, empirical proof that permeability was the absolute deciding factor between survival and fragmentation. They knew exactly how the failure occurred. They knew exactly why it occurred. They mathematically proved that the lower intensity skip trajectory was actively generating explosive internal pressure within the non-permeable blocks. And yet, instead of halting the program to rebuild the Artemis II heat shield with a permeable architecture, the agency began searching for a way to simply endure the fragmentation. Part 8. The Margin of Survival. Underneath the ablative armor of the Orion spacecraft lies the last line of defense between human tissue and a 5000-degree plasma wake. It is not an impenetrable wall of steel. It is a highly engineered carrier structure comprised of a titanium orthogrid skeleton overlaid with a carbon fiber composite skin. It is lightweight, it is structurally brilliant, it is physically incapable of surviving direct exposure to re-entry heat. Here is why this matters. In the unforgiving math of aerospace engineering, survival is dictated by a concept called margin. Margin is the difference between the maximum predicted stress a component will endure and the point at which that component physically disintegrates. It is the mathematical buffer zone. It is the unbreachable red line. For the Artemis heat shield, the margin is strictly defined by the thickness of the virgin Avcoat remaining after the vehicle slashes through the atmosphere. At its thickest point, that layer of resin is barely 3 inches deep. At its thinnest, it is closer to 1.6 inches. That is the entire physical distance between survival and incineration. When NASA publicly addressed the Artemis I anomaly, they maintained a posture of bureaucratic reassurance. They pointed to the telemetry. They emphasized that despite the widespread spallation, the violent ejection of thick, unpredicted chunks of material, a layer of virgin Avcoat ultimately remained intact across the base of the capsule. They declared the margin was healthy. They declared the vehicle was safe. But safety, when dealing with explosive fragmentation at Mach 32, is a statistical illusion. Let's be precise about what this means. An ablative shield designed to melt smoothly provides a mathematically predictable margin. A shield that unpredictably detonates in solid chunks completely destroys that predictability. When those jagged pieces blew off the Artemis I shield, they did not politely stop at a predetermined depth. They chewed violently into the safety buffer. In several specific locations, the localized margin plummeted towards zero. We know this because of the physical evidence left at the separation hardpoints. Embedded deep within the heat shield are 4 heavy mechanical bolts, required to physically sever the shield from the crew cabin just before splashdown. These bolts sit in deeply recessed pockets, protected by their own dedicated thermal barriers. They are supposed to remain buried safely beneath the intact char layer for the entirety of the descent. But the unpredicted spallation gouged so deeply into the surrounding Avcoat that these localized thermal barriers were suddenly exposed to the raw, unmitigated slipstream. The plasma rushed into the newly formed craters. It pooled. It aggressively attacked the hardware. 3 of those 4 massive separation bolts partially melted through. Think of it like a deep-sea submarine. If you design a steel hull to withstand 1,000 feet of pressure, and you return from a dive to find erratic, jagged gouges carved violently into the outer plating, you do not celebrate the fact that the inner lining narrowly held. You realize how close you came to drowning. If the spallation had plunged just a fraction of an inch deeper in those critical locations, the result would not have been a damaged heat shield. The result would have been hot gas ingestion. Hot gas ingestion is the sterile academic term for a nightmare. It means the 5000-degree plasma violently breaches the protective resin and physically touches the underlying carbon fiber and titanium skeleton. Titanium melts at roughly 3000 degrees Fahrenheit. The plasma is 5000 degrees. The mathematical equation is absolute. The titanium orthogrid would instantly yield. The superheated gas would flood the interior gap between the shield and the crew cabin. The vehicle would violently unzip from the bottom up in a matter of seconds. Stay with me for a moment. Let that sink in. The boundary between a successful test flight and the total structural disintegration of the Orion capsule was not guaranteed by brilliant engineering or sound physics. It was dictated by sheer, unadulterated luck. The fragmentation stopped just millimeters short of a catastrophic thermal breach, entirely by accident. The The physical hardware survived the descent, the engineering margin did not. Part 9. The Ghost of Columbia. In the hallways of the Johnson Space Center, there is a specific physical phenomenon that engineers do not speak about in the abstract. They speak about it with a deeply ingrained institutional grief. It is the phenomenon of unpredicted solid debris interacting with a thermal protection system at hypersonic velocities. It is the ghost of STS-107, Space Shuttle Columbia. Here is why this matters. To understand the gravity of the Artemis I heat shield anomaly, we must look backward at the exact aerodynamic mechanism that tore Columbia out of the Texas sky on the morning of February 1st, 2003. Now, intellectual honesty demands we draw a strict physical line between these two vehicles. Let us be precise about what is not connected. Columbia did not shed ablative material on re-entry. Columbia was mortally wounded during liftoff when a suitcase-sized piece of insulating foam fell from the external fuel tank and struck the reinforced carbon-carbon panels on the leading edge of the left wing. Artemis I shed its material entirely during the descent phase. The origins of the debris are fundamentally different, but the physics of the consequence are terrifyingly identical. The Columbia disaster was, at its core, a failure of margin caused by unanticipated localized damage. When that foam struck the shuttle's wing, it did not destroy the entire vehicle. It simply punched a hole, a microscopic breach in the continuity of the thermal armor. For 16 days in orbit, the crew was perfectly safe. The vehicle operated flawlessly, but the structural margin of the heat shield had been secretly reduced to zero in one isolated location. When Columbia hit the atmosphere at Mach 18, the 5,000-degree plasma did exactly what fluid dynamics dictates it must do. It found the anomaly. It flowed into the breach. It pooled inside the leading edge of the wing, instantly melting the underlying aluminum structure from the inside out. The plasma found the gap. The margin collapsed. The vehicle disintegrated. Think of it like a dam holding back a reservoir. The concrete face of the dam does not need to completely collapse for a catastrophic flood to occur. A single, localized fissure that allows pressurized water to penetrate the interior structure will rapidly widen until the entire system violently fails. When engineers stared at the cratered landscape of the Artemis I heat shield, they were staring at the exact same physical threat. The Avcoat spallation did not occur as a gentle dusting of particles. The shield aggressively liberated thick, heavy, solid blocks of resin into the Mach 32 slipstream. And just as the engineers could not predict where the foam would strike Columbia, the thermal analysts could not predict exactly where, when, or how deeply the Avcoat would fracture on Artemis. The mechanism was entirely unmodeled. It was entirely unpredictable. It was fundamentally out of their control. Let's be precise about what this means for a crewed mission. If an ablative shield fractures and sheds a chunk of material just upstream of a critical structural junction, like the thermal barriers protecting those vital separation bolts, that newly formed crater radically alters the aerodynamic flow of the plasma. The sheer face of the missing chunk creates a microscopic eddy. The superheated gas swirls into the cavity, stalling and concentrating its thermal energy in a concentrated hotspot. This is not a theoretical model. This is exactly what the physical evidence on the Artemis I shield demonstrated. The plasma found the newly formed topographical valleys. It attacked the hardware. It partially melted the bolts. The Artemis engineers were watching the Columbia mechanism recreate itself, step by step, entirely by accident. Stay with me for a moment. Let that sink in. The space agency had spent 2 decades meticulously engineering a capsule to replace the space shuttle, vowing to never again fly a vehicle where solid debris could unexpectedly compromise the thermal protection system. And yet their brand new multi-billion-dollar spacecraft had just returned from its maiden voyage, having actively generated its own catastrophic debris field. The vehicle had essentially assaulted its own armor. Part 10. The Challenger Echo. Sociologist Diane Vaughan coined a specific, highly academic phrase to describe the culture inside NASA leading up to the loss of the Space Shuttle Challenger in 1986. She called it the normalization of deviance. Here is why this matters. The Challenger disaster was not caused by a sudden, unpredictable lightning strike of bad luck. It was a slow, bureaucratic suicide. For years prior to the explosion, engineers knew the rubber O-rings in the solid rocket boosters possessed a fundamental design flaw. During multiple successful shuttle launches, hot propellant gases had bypassed those rings, causing deeply concerning localized damage. But because the shuttle returned safely each time, the institutional mindset slowly shifted. A terrifying structural anomaly was gradually redefined in meeting rooms as an acceptable flight risk. They survived a flaw, so they assumed the flaw was safe. This is the normalization of deviance. It is the gradual process through which unacceptable practice becomes the baseline operating standard simply because a catastrophe hasn't happened yet. And when engineers stared at the cratered landscape of the Artemis I heat shield, they were watching this exact sociological phenomenon resurrect itself in real time. Let's be precise about what this means. The spallation of the Avcoat material on Artemis I was entirely unmodeled. It was a violent, unpredictable fragmentation of the primary thermal protection system. By every fundamental historical principle of aerospace safety, an unmodeled fragmentation event on a heat shield is an absolute no-go for human spaceflight. It demands a complete halt to the program until the root cause is engineered out of existence. But NASA did not halt the program to redesign the Artemis II hardware. Why? Because of the immovable, brutal gravity of the launch schedule. The Artemis program is not just a scientific endeavor, it is a geopolitical mandate. It is a multi-billion-dollar apparatus, scrutinized by Congress, audited by the Government Accountability Office, and locked in a deeply public race against international timelines. The GAO has explicitly reported that the infrastructure and ground systems supporting these missions are operating with absolutely zero schedule margin. The operational buffer is completely gone. Every single delay compounds. Every single delay pushes the highly anticipated Artemis III lunar landing further toward the end of the decade. To rip out the flawed solid block Avcoat heat shield from the Artemis II capsule and replace it with a properly vented, honeycomb architecture would require completely disassembling a spacecraft that was already constructed. It would introduce a multi-year delay. It was a timeline the agency believed it could not politically or financially survive. So, the bureaucracy did what bureaucracies do. It began to rationalize the anomaly, because the Artemis I crew cabin did not physically incinerate, because the localized margin had narrowly held and the separation bolts only partially melted. Management began to view the unpredicted spallation not as a fatal flaw, but as a survived event. The language inside the agency shifted. The narrative moved away from fixing the physical chemistry of the shield and toward managing the statistical probability of the fragmentation. Stay with me for a moment. Let that land. The space agency was actively deciding to launch 4 human beings on a vehicle possessing a known, unpredictable structural anomaly, justified largely by the fact that the mannequins on the previous flight didn't die. It is a sobering echo of the exact institutional behavior that killed 7 astronauts in 1986. During the Challenger investigation, the brilliant physicist Richard Feynman famously condemned this exact type of bureaucratic rationalization. He warned the agency that when you play Russian roulette, the fact that the first shot got off safely is little comfort for the next. NASA was looking down the barrel of a Mach 32 re-entry. They knew there was a bullet in the cylinder, but the schedule demanded they pull the trigger anyway. Part 11. The Voice of Dissent. When an institution decides to normalize a catastrophic hardware anomaly, the burden of truth falls to the individuals willing to risk their legacies to point it out. Enter Dr. Charles Camarda. Here is why this matters. Camarda is not an armchair critic, a disgruntled contractor, or an outsider guessing at aerodynamic physics. He holds a PhD in aerospace engineering. He served as the Director of Engineering at NASA's Johnson Space Center. He is one of the world's preeminent experts in thermal protection systems. But most importantly, he is a former Space Shuttle astronaut. He was selected to fly on STS. He strapped into the Space Shuttle Discovery in 2005, the very first crewed launch after the Columbia disaster. He intimately, deeply understands the physical and psychological cost of ignoring heat shield vulnerabilities. He has looked into the eyes of the families left behind by motivated reasoning. When NASA leadership declared the fragmented Artemis II heat shield an acceptable risk, Camarda broke ranks. He became the loudest warning siren in the aerospace community. His argument was unsparing, and it was rooted entirely in the physical evidence. Camarda explicitly rejected the agency's narrative that the Avcoat was an unbroken, reliable Apollo legacy. He pointed back to the 1960s. noting that the original Apollo engineers fully understood the structural limitations of the resin. They knew that solid monolithic blocks of Avcoat would undergo a chaotic physical transition during a 5,000 re-entry, shifting unpredictably between a brittle, charred outer crust, a gooey, viscoelastic middle layer, and a dense, solid base. Let's be precise about what this means. The physical strength of the material varies by orders of magnitude across mere inches of depth. Think of it like dropping a frozen, solid candy bar into a deep fryer. The outside shatters, the inside turns to liquid, and the core remains rock hard. It is mathematically impossible to accurately predict how a violent, supersonic crack will propagate through a solid block, experiencing those extreme, contradicting states all at once. The Apollo engineers recognized this mathematical impossibility. That is exactly why they mandated the labor-intensive fiberglass honeycomb matrix to act as natural, physical crack arresters. By stripping that structural skeleton out to save time and manufacturing costs, Camarda argued, the modern Artemis program had unknowingly resurrected a fatal physical flaw the Apollo generation had already engineered out of existence. NASA management dismissed his warnings. They pointed to their computer simulations. They claimed the adjusted flight trajectory would solve the internal pressure issue. Camarda's response was brutal. He accused the agency of building toy models. If you build a computer simulation to predict how a hurricane will behave, but you input the wrong barometric data, the software will output a beautiful, mathematically perfect model of a storm that doesn't actually exist. Camarda argued that NASA's analytical models were built on fundamentally flawed assumptions about how this specific, newly modified Avcoat responds to a lunar thermal profile. You cannot use software to prove a material is safe when the physical material has already violently proved it is not. He labeled the Orion underbelly a deviant heat shield. He bluntly stated that the agency does not know how it will fail, and they do not know how to predict its failure. In January of 2026, NASA leadership convened a meeting to discuss the Artemis II launch decision. Camarda was invited, alongside journalists, but instead of a rigorous, open technical debate, he found a choreographed public relations event. The decision to fly a crew had already been finalized. He was present not to argue the physics, but to lend a veneer of transparency to an immovable bureaucratic decree. Stay with me for a moment. Let that land. The agency responsible for human spaceflight had just sidelined one of their most decorated, experienced thermal experts. They opted to trust a computer model that had already been proven wrong by the Artemis I hardware, rather than listen to the engineer who had physically staked his own life on a heat shield exactly 2 years after an identical bureaucratic process killed 7 of his colleagues. The math was catastrophic. The warnings were clear. The descent was documented, and the launch countdown continued anyway. Part 12. The bureaucratic calculus. When a multi-billion-dollar aerospace architecture fails physically, the institution will inevitably attempt to save it mathematically. Here is why this matters. To justify strapping 4 astronauts into the Artemis II capsule without replacing the compromised heat shield, NASA leadership could not simply cross their fingers. They needed a defensible, bureaucratic rationale. They needed numbers. They convened a specialized group of engineers, a Tiger team, tasked with quantifying the exact probability of a catastrophic thermal breach. Their objective was not to fix the material science of the Avcoat resin. Their objective was to mathematically prove the fragmentation could be survived. They turned to analytical software. Specifically, they utilized lumped parameter models and a predictive system internally referred to as the crack indicator tool. Let's be precise about what this means. A lumped parameter model is a simplified mathematical simulation. It takes a complex physical system and reduces it to a series of discrete, generalized variables. It is highly effective for basic thermodynamic calculations, but it is fundamentally structurally blind to the chaotic microscopic realities of a 5,000 hypersonic shockwave. The Artemis II Tiger team used these simplified models to simulate the Avcoat's behavior under a newly proposed, less severe re-entry trajectory. They inputted the thermal loads. They inputted the density of the resin. They calculated the theoretical buildup of internal hydrocarbon gases. The software outputted a clean, conservative margin. The models declared that while the heat shield would likely still fragment, the spallation would not penetrate deeply enough to expose the titanium skeleton. They mathematically bounded the problem. But in the uncompromising discipline of fluid dynamics, the math was built on a fiction. Think of it like this. Imagine trying to predict the exact shape, depth, and trajectory of a shattered pane of glass using only a pocket calculator. You might know the velocity of the rock that hit it, but you cannot model the microscopic flaws in the glass itself. The math is irrelevant if the material is fundamentally chaotic. The solid blocks of modern Avcoat do not possess a single uniform physical state during re-entry. The extreme heat forces the material to transition violently through 3 distinct phases at the exact same time. The outer surface is a brittle, porous char. The middle layer is a gooey, viscoelastic transition zone. The inner core is dense, unyielding resin. The physical strength of the heat shield varies by orders of magnitude across mere inches of depth. It is mathematically impossible for a simplified, lumped parameter model to accurately predict how a violent, supersonic fracture will propagate through a solid block experiencing those extreme, contradicting states simultaneously. The multiphysics are simply too complex. The simulation was predicting how a uniform material should behave, while the actual hardware had already physically proven it behaves unpredictably. The NASA Office of Inspector General recognized this exact analytical vulnerability. In their formal audits of the Artemis program, the OIG delivered a deeply sobering assessment. They noted that NASA's strategy to reuse the compromised heat shield design on Artemis II was heavily reliant on altering the flight trajectory to explicitly avoid the specific thermal soaking that triggered the Artemis I anomaly. The OIG explicitly stated that this approach is technically complex, contingent entirely on an unproven flight profile, and critically, it does not retire the heat shield risk. It is risk management. It is not risk elimination. Stay with me for a moment. Let that land. The official independent watchdog of the space agency formally documented that the primary defense mechanism of the spacecraft still possesses an active, unretired risk of structural failure. The bureaucratic calculus was complete. NASA leadership, looking at a schedule completely devoid of operational margin and a geopolitical mandate they could not delay, accepted the risk. They chose to trust a simplified software simulation over the physical created reality of the Artemis I hardware. They declared the vehicle safe for human flight. The math was approved. The hardware remained exactly the same. Part 13. The Artemis II Compromise. When the simplified mathematical models were finalized and the dissenting voices were officially sidelined, a stark, physical reality remained. NASA was not debating a blueprint. They were debating a fully constructed machine. Here is why this matters. When the Artemis I capsule returned to Earth in late 2022, with its shattered thermal armor, the Artemis II crew module was already largely assembled inside the operations and checkout building in Florida. The deeply flawed solid block Avcoat heat shield was already physically bolted to the titanium skeleton of the spacecraft that would carry the next human crew. To correct the fundamental chemical and structural flaw, to return to the proven breathable honeycomb architecture of the Apollo era, NASA would have to order a massive deconstruction. Let's be precise about what this means. They would have to halt the assembly line. They would have to meticulously detach the 16.5-foot heat shield from the base of the crew cabin. They would have to discard the multi-million-dollar component entirely. Then they would have to initiate a multi-year development cycle to redesign, remanufacture, and recertify an entirely new thermal protection system from scratch. Aerospace analysts estimated this process would inject a minimum of 2 to 3 years of delay into a program that was already violently bleeding time and money. The schedule was an unforgiving tyrant. A 3-year delay to Artemis II would cause a cascading collapse of the entire lunar architecture. Artemis III, the mission slated to physically land Americans on the surface of the moon to counter rapid international competition, would be pushed to the end of the decade or perhaps into the 2030s. The geopolitical optics were considered catastrophic. The congressional funding was entirely precarious. Faced with the choice of destroying the launch schedule or accepting a known physical anomaly, the bureaucracy made its final calculation. They chose to keep the compromised heat shield. They did not change the chemistry, they did not change the architecture. They changed the flight path. The official institutional decree was that Artemis II would fly with the exact same solid block Avcoat design that had violently fragmented on Artemis I. The agency's stated mitigation was to utilize a modified skip guidance re-entry trajectory. a flight path explicitly engineered to be slightly less thermally severe, in the desperate hope that it would generate less internal pressure inside the resin blocks. They were not removing the physical risk. They were attempting to carefully tiptoe around it. Think of it like discovering the brake lines on your car are structurally prone to bursting under heavy pressure. And instead of replacing the lines, you simply mandate that the driver must never press the pedal past halfway. It is a procedural band-aid applied to a fundamentally mechanical wound. But this time, the payload was not a collection of sensor-laden mannequins. The payload was Reed Wiseman, a highly decorated naval aviator and former chief of the astronaut office. It was Victor Glover, a test pilot with over 3,000 hours of flight experience and 24 combat missions. It was Christina Koch, a brilliant electrical engineer holding the record for the longest single spaceflight by a woman. And it was Jeremy Hansen, a Royal Canadian Air Force fighter pilot, representing the international coalition of the Artemis Accords. These are four of the most heavily trained, deeply capable human beings on the planet. They are test pilots and scientists who understand the mathematics of risk intimately. When they accepted the mission, they knew they were stepping into a vehicle that was functionally a prototype. But there is a vast, unbridgeable chasm between the inherent, unavoidable dangers of spaceflight and the institutional normalization of a known, unretired structural failure mechanism. Stay with me for a moment. Let that sink in. The smartest aerospace engineers on Earth had irrefutable physical evidence that their primary thermal protection system could violently explode from the inside out at Mach 32. And the official strategy for keeping 4 human beings alive was to bet that the explosion wouldn't be quite deep enough to incinerate the titanium hull. The decision was locked in. The heat shield remained bolted to the capsule. The hardware was officially declared ready for flight, not because it was perfect, but because the schedule demanded it. Part 14. The Trajectory Band-Aid. You cannot fix a fractured physical armor with a navigational command. But in the architecture of the Artemis II mission, a procedural software adjustment is exactly what is standing between the crew and a hypersonic thermal breach. Here is why this matters. When an aerospace engineer identifies a fatal material flaw, like a solid resin that chokes on its own gas and detonates, the orthodox, uncompromising solution is to redesign the material. But NASA had already committed to flying the flawed Avcoat blocks. The hardware was bolted to the capsule. The geopolitical launch schedule was closing in. So, the agency engineered a workaround. They decided they could not change the physical behavior of the heat shield, but they could change the physical environment the heat shield was exposed to. They altered the geometry of the fall. To understand the sheer audacity of this compromise, we must look back at the Artemis I flight profile. The original brilliance of the Orion spacecraft was its skip re-entry, the graceful double bounce maneuver that allowed the capsule to bleed off speed slowly. That skip was designed specifically for human survival. It drastically lowered the punishing gravitational forces exerted on the astronauts' bodies, keeping the G-loads well within a safe, comfortable margin. But as the physical evidence proved, that very same gentle, high-altitude glide allowed the thermal energy to soak deep into the uncharred Avcoat blocks, building catastrophic internal pressure until they exploded on the second plunge. NASA's solution for Artemis II was brutal in its simplicity. Eliminate the long skip. Instead of allowing the capsule to bounce back out of the atmosphere to cool down, the Artemis II trajectory was reprogrammed to execute a significantly steeper, vastly more aggressive descent angle. They are forcing the vehicle to plunge deeper and faster. Let's be precise about what this means. By coming in steeper, the capsule spends far less time in that deceptive, high-altitude transitional phase. The outer surface of the Avcoat is subjected to an immediate, unrelenting wall of maximum plasma heat, flash baking the resin into a porous char layer before the internal gases have the time to accumulate and build pressure. They are essentially attempting to outrun the explosion. Think of it like running across a frozen lake with fracturing ice. If you stop or slow down, the structural integrity beneath your feet collapses. The only way to survive is to sprint directly to the other side, trusting that momentum will carry you across before the physics catch up with you. NASA is relying entirely on a steeper angle of attack to artificially force the heat shield to behave. But in aerospace, every single aerodynamic action demands an equal and unforgiving physical toll. You cannot cheat the conservation of energy. The kinetic energy of a spacecraft traveling at 25,000 miles per hour must be dissipated. If you eliminate the long, gentle skip that was engineered to bleed off that energy slowly, that energy must now be violently absorbed in a much shorter window of time. By steepening the descent to protect the fragile heat shield, NASA is shifting the physical burden of deceleration. The vehicle will decelerate much faster. The aerodynamic braking will be exponentially more violent, and the 4 human beings strapped into the crew cabin will absorb the difference. The G-forces acting upon Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen will spike. The physical trauma of the return will be definitively harsher. Stay with me for a moment. Let that sink in. The original flight profile was meticulously engineered to protect the soft tissue of the human body, but it destroyed the machine. The revised flight profile is meticulously engineered to protect the machine, but it physically punishes the human body. The Office of Inspector General reviewed this trajectory modification and delivered a quiet, devastating verdict. They formally noted that while this steeper descent is technically feasible and might successfully minimize the child liberation, it does not retire the heat shield risk. The physical flaw in the Avcoat blocks remains completely intact. The agency is simply gambling that they can thread the needle of orbital mechanics so perfectly that the flaw is never violently triggered. Part 15. The Artemis III admission. In aerospace engineering, the truth is not found in press releases. It is found in the supply chain. When an agency declares a piece of critical safety hardware to be completely reliable, they do not immediately dismantle its blueprint for the very next flight. They mass produce it. They standardize it. They lock the design in. But if you look past the public assurances surrounding the Artemis II launch and examine the manufacturing flaw for the subsequent mission, Artemis III, you will find the most damning piece of institutional evidence in this entire saga. Here is why this matters. NASA has quietly officially confirmed that the Artemis III spacecraft will not fly with the same heat shield as Artemis II. They are fundamentally altering the design. Let's be precise about what this means. The agency spent months publicly arguing that the solid block Avcoat on Artemis II, combined with a steeper descent trajectory, creates a mathematically safe vehicle. They assured the astronauts, the oversight committees, and the public that the fragmentation anomaly is a managed, acceptable risk. And yet, for the mission immediately following it, they are actively changing the chemistry and the structure of the Avcoat to explicitly restore the very permeability they claim Artemis II can live without. Think of it like an automotive manufacturer identifying a fatal flaw in the brakes of their new sedan. They tell the customer who already bought the car that it is perfectly safe to drive as long as they never brake on a downhill slope. But simultaneously on the factory floor, they are radically redesigning the brakes for next year's model to ensure the flaw no longer exists. It is a silent, absolute admission that the original design was fundamentally inadequate. If the solid blocks are safe, you fly the solid blocks. You do not spend hundreds of millions of dollars to engineer a fix for a problem you claim is already solved. The Artemis III heat shield is being manufactured with deliberate architectural changes to allow the expanding hydrocarbon gases to vent naturally during a 5,000 thermal soaking. The engineers are returning to the baseline physics of ablation. They are building a shield that sweats, rather than a shield that detonates. They are actively correcting the exact structural vulnerability that Charles Camarda and the dissenting thermal experts warned them about. But this redesigned, permeable armor will not be ready in time for Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen. Stay with me for a moment. Let that sink in. NASA possesses the engineering capability to fix the heat shield. They know exactly how to do it. They are literally in the process of doing it right now. But because the Artemis II vehicle was already assembled, and because the geopolitical mandate refuses to tolerate a multi-year delay to unbolt and replace the flawed component, the current crew is being forced to fly the prototype. The agency is operating under a deeply fractured logic. They have implicitly acknowledged that the Artemis II thermal protection system is not safe enough to become the baseline standard for human lunar exploration. It is a one-off compromise. It is a recognized temporary deficiency. The decision to change the Artemis III design strips away the final layer of bureaucratic defense. It proves, beyond a shadow of a doubt, that launching the Artemis II crew on the fragmented Avcoat design was never a decision driven by sound material science. It was entirely a decision driven by the clock. Part 16. The schedule squeeze. To understand why a space agency would gamble human lives on a compromised heat shield, you have to stop looking at the physics and start looking at the calendar. Here is why this matters. A spacecraft is not built in a vacuum. It is built inside a geopolitical pressure cooker. When Artemis I landed and the fatal flaw in the solid block Avcoat was discovered, the thermal engineers were not the ones who decided the ultimate fate of Artemis II. The accountants and the politicians did. Let's be precise about what a hardware redesign actually requires. You cannot simply swap a 16.5-foot composite heat shield like a tire on a car. The Artemis II crew module was already fundamentally assembled inside the operations and checkout building. To replace the flawed solid blocks with a proper breathable honeycomb matrix, NASA would have to execute a catastrophic deconstruction. They would have to halt the entire assembly line. They would have to decouple the shield, scrap the component, and stand up an entirely new, labor-intensive manufacturing process. Aerospace analysts estimated this single hardware correction would inject a minimum of 3 years of delay into the Artemis II mission. In the unyielding math of federal spaceflight, a 3-year delay is an institutional death sentence. Think of it like this. The Artemis program does not operate on a fixed budget, it operates on a standing army. Thousands of engineers, specialized contractors and technicians must be paid every single day the rocket sits on the ground. A blistering report from the Government Accountability Office, the independent watchdog of the United States government, calculated that a single Artemis launch costs roughly $4 billion. A 3-year pause to fix a composite resin would incinerate billions of dollars in pure operational burn rate before the vehicle ever left the pad. But the financial hemorrhage was only half the problem. The true, immovable object was China. While NASA was staring at the fractured, cratered chunks of the Artemis I heat shield, the China Manned Space Agency was rapidly advancing. China has publicly, officially locked in their mandate. They will land human beings on the surface of the moon by the year 2030. They are testing their next-generation rockets. They are building the Lanue lunar lander. They are moving with terrifying, unbroken momentum. Stay with me for a moment. Let that land. If NASA halted Artemis II for 3 years to physically guarantee the safety of the heat shield, the mission would mathematically slip into the late 2020s. Consequently, Artemis III, the actual historic lunar landing mission, would be forced deep into the 2030s. The United States would lose the race to the lunar South Pole. The geopolitical high ground of the 21st century would be ceded to a foreign superpower simply because an American heat shield could not properly vent its own gas. The agency determined that this scenario was completely organizationally unsurvivable. If they lost the race, they risked losing their congressional funding. If they lost the funding, the Artemis program would collapse entirely. They were trapped. The uncompromising laws of fluid dynamics demanded a multi-year delay, but a geopolitical mandate demanded immediate flight. So, NASA leadership made the only calculation a terrified bureaucracy knows how to make. They protected the schedule, they looked at the unpredicted fragmentation, they looked at the partially melted separation bolts, and they officially concluded that the timeline was more fragile than the hardware. The flawed heat shield would remain exactly as it was. The delay was rejected, the launch schedule survived. Part 17. The normalization of deviance. In 1996, a sociologist named Diane Vaughan published a post-mortem of the Space Shuttle Challenger disaster that fundamentally changed how aerospace engineers view their own psychology. She identified a phenomenon so insidious it can bring down a multi-billion-dollar space program without a single mathematical error being made. She called it the normalization of deviance. Here is why this matters. Vaughan discovered that Challenger did not explode because NASA lacked data. It exploded because the agency gradually, culturally redefined what dangerous data meant. For years leading up to the disaster, hot propellant gases had routinely bypassed the solid rocket booster O-rings. Because the shuttle safely returned each time, the institutional mindset slowly shifted. A terrifying structural anomaly was gradually reclassified in committee meetings as a baseline operating condition. They survived a fatal flaw, so they assumed the flaw was not fatal. When you examine the bureaucratic architecture of the Artemis II launch decision, you are not watching a new era of space exploration. You are watching Diane Vaughan's textbook definition of deviance perfectly recreate itself, step by step, in the 21st century. Let's be precise about what this means. By every historical metric of human spaceflight, an unmodeled fragmentation event on a primary thermal protection system is an immediate loss of crew threat. When the Office of Inspector General released its investigation into the Artemis I anomaly, they specifically outlined 3 catastrophic mechanisms spalling that could expose the titanium hull to 5,000-degree plasma, liberated debris that could violently strike the parachute compartments, and hot gas ingestion caused by the melted separation bolts. Any single one of those 3 mechanisms is a death sentence for a spacecraft. But because the Artemis I capsule ultimately splashed down in the Pacific without the mannequins inside, turning to ash, the institutional narrative immediately began to pivot. The physical reality of the cratered heat shield was slowly buried underneath a mountain of probabilistic risk assessments. The Tiger teams were not tasked with proving the shield wouldn't break. They were tasked with mathematically arguing that when it did break, it probably wouldn't break deeply enough to kill anyone. Think of it like this. Imagine discovering a hairline fracture in the foundation of a massive hydroelectric dam. The orthodox engineering response is to drain the reservoir and pour new concrete. The normalization of deviance is choosing to leave the water at full capacity, building a computer model to estimate exactly how much water the crack will leak before the dam bursts, and then declaring the crack an acceptable risk because the model says you have a few inches of safety left. The physical vulnerability remains completely active. Only the paperwork has changed. This is the creeping normality of the Artemis program. The agency has convinced itself that, because they mathematically bounded the problem with a steeper re-entry trajectory, they have controlled the danger. They have convinced themselves that stripping away the operational margins of the hardware is acceptable because the international geopolitical schedule allows for zero delay. They have taken off their engineering hats. They have put on their management hats. Stay with me for a moment. Let that sink in. The space agency is officially flying an uncrewed flight test design with a crewed payload, explicitly relying on a procedural band-aid to mitigate a known structural failure, while simultaneously redesigning the entire system for the mission immediately following it. That is not risk elimination, that is the institutional acceptance of Russian roulette. They are no longer engineering for certainty, they are engineering for luck. Part 18. The human payload. A spacecraft fundamentally changes its definition the moment the hatch seals behind a crew. An uncrewed test vehicle is an assembly of titanium, carbon fiber, and telemetry data. A crewed spacecraft is an ethical contract. Here is why this matters. The bureaucratic decision to launch Artemis II without replacing the structurally flawed Avcoat heat shield is not an academic exercise in risk management. It is a decision that physically applies the violent, unpredictable multiphysics of a compromised thermal armor to human biology. To understand the sheer weight of this gamble, we must examine the specific human capital strapped into the Orion capsule. This is not a standard passenger manifest. This is arguably the most capable, deeply experienced, and heavily vetted flight crew assembled in the modern era of spaceflight. Reed Wiseman is the commander. He is a United States Navy captain and a highly decorated naval aviator. He served as the chief of the astronaut office from 22,000 to 22,002. Let's be precise about what this means. Wiseman was the individual responsible for managing astronaut training and flight assignments for the entire space agency. He is the ultimate arbiter of operational safety. He has spent his entire career evaluating the razor-thin margins between acceptable flight risk and catastrophic negligence. Victor Glover is the pilot. He is a United States Navy captain holding multiple master's degrees in flight test engineering and military operational art. He has logged over 3,000 hours in high-performance aircraft, including 24 combat missions in the FA-18 Hornet. He was the pilot for the historic SpaceX Crew 1 mission, the very first operational commercial crew flight to the International Space Station. He understands the brutal, uncompromising physics of atmospheric re-entry intimately. Christina Koch is a mission specialist. She is a brilliant electrical engineer who honed her operational discipline maintaining scientific instruments in the freezing, remote desolation of Antarctica and Greenland. She holds the absolute world record for the longest single spaceflight by a woman, having spent 328 continuous days in the microgravity environment of the orbital laboratory. She intimately understands the limitations and the fragilities of deep space life support systems. Jeremy Hansen is the second mission specialist. He is a colonel and a fighter pilot in the Royal Canadian Air Force, representing the international coalition of the Artemis Accords. He is a deeply respected leader within the global astronaut community, having served extensively as a capsule communicator, the vital operational voice bridging the vacuum of space with the engineers on the ground. They are analytical, they are brilliant, they are physically trapped. Think of it like this. In the cockpit of an FA-18 or the flight deck of a space shuttle, a highly trained pilot possesses agency. If a navigation computer glitches, they can manually override the system. If an automated docking sequence fails, they can fly the vehicle by hand. If a life support valve sticks, they can physically bypass it. They can use their thousands of hours of training to actively mitigate an unfolding disaster. But you cannot pilot your way out of a thermal breach. When the Orion capsule hits the upper atmosphere at 24,500 miles per hour, the crew is entirely at the mercy of the material science beneath them. If the steepened flight trajectory fails to prevent the internal gas pressure from building, and the solid block Avcoat violently detonates again, no amount of combat flight experience will save them. They cannot rebuild a fractured composite resin block at Mach 32. Their survival is entirely passive. Now, intellectual honesty demands we draw a strict line here. Let us state precisely what is not happening. These four individuals are not being marched blindly to the launch pad against their will. They are not naive victims of a bureaucratic cover-up. They have seen the data. They are exceptional test pilots who have willingly accepted the immense inherent dangers of riding a controlled explosion into the vacuum of space. But accepting the inherent, unavoidable dangers of spaceflight is fundamentally different from accepting a known, unretired hardware failure mechanism that the agency literally intends to engineer out of existence for the very next mission. Stay with me for a moment. Let that sink in. The agency has taken the absolute finest operational minds of their generation, placed them inside a vehicle possessing a recognized, catastrophic structural vulnerability, and asked them to bet their lives that a steeper fall through the atmosphere will keep the plasma just a few millimeters away from their flesh. They have dedicated their lives to the advancement of human knowledge, willingly accepting the terrifying physics of orbital mechanics. But they are flying on a compromised shield. Part 19. The Anatomy of a Gamble. To understand how a premier space agency justifies launching a structurally flawed spacecraft, you must understand the mathematical language of acceptable losses. It is a discipline known formally as probabilistic risk assessment, or PRRA. Here is why this matters. In the early days of the Apollo era, the engineering philosophy was largely deterministic. If a critical component demonstrated a physical failure mechanism during testing, the component was redesigned until that physical failure mechanism no longer existed. The hardware had to be absolute. But as spaceflight became exponentially more complex and budgets became tightly constrained, NASA adopted PRA, a quantitative, statistical tool originally developed by the commercial nuclear power industry to calculate the exact likelihood of reactor meltdowns. PRA does not fix physical problems, it calculates them. Let's be precise about what this means. A probabilistic risk assessment takes a complex spacecraft and attempts to assign a numerical probability to every conceivable failure, rolling those numbers up into a final, sterile metric known as loss of crew. The institutional goal is no longer to build a perfect, unbreakable machine. The goal is to build a machine where the mathematical probability of death falls below a pre-approved bureaucratic threshold. Think of it like this. If you discover the parachute on your rig has a severely frayed cord, deterministic engineering dictates you replace the entire cord before you jump. Probabilistic engineering dictates you calculate the exact tensile strength of the fray, calculate the expected wind shear, and if the software suggests the cord will only snap 1 out of every 500 jumps, you declare the parachute safe for flight. It is risk management. It is not risk elimination. When NASA leadership was confronted with the physical reality of the Artemis I heat shield violently blowing itself apart, they did not return to deterministic engineering. They did not halt the assembly line to replace the fatal flaw. They turned to the PRA models. The Tiger teams fed the data of the unpredicted spallation into the software. They modeled the melted separation bolts. They modeled the deep, erratic gouges. And they found that if they flew the original long-skip re-entry profile with a human crew, the mathematical probability of a fatal thermal breach was undeniably, catastrophically high. So, they introduced the trajectory band-aid by programming the Artemis II spacecraft to execute a significantly steeper, more violent plunge into the atmosphere, they were not structurally repairing the solid Avcoat blocks. They were simply attempting to manipulate the variables in their statistical software. The steeper trajectory lowered the theoretical heat-soak time, which theoretically reduced the internal gas pressure, which theoretically lowered the mathematical probability of a loss of crew event just enough to satisfy the spreadsheet. Stay with me for a moment. Let that land. The space agency is not betting 4 human lives on the physical structural strength of the heat shield. They are betting on the accuracy of a statistical computer simulation that is attempting to model a chaotic 5,000-degree explosive fragmentation event that their own most senior thermal experts explicitly admit they cannot predict. They replaced a physical margin of safety with a mathematical margin of probability. The vehicle is compromised, the schedule is uncompromising, the math is a gamble. Part 20. The point of no return. Right now, suspended in the silent, freezing vacuum of space, the Artemis II capsule is falling toward Earth. Inside the crew cabin, the environment is perfectly sterile. The telemetry screens hum with nominal data. The communications link with mission control is steady, measured, and profoundly calm. But the bureaucratic phase of this mission is over. Here is why this matters. For years, the survival of this crew was debated in climate-controlled conference rooms. It was negotiated by tiger teams. It was calculated by predictive software models. The space agency utilized every tool of modern management to mathematically justify the structural integrity of the Avcoat resin. They adjusted the flight path. They protected the schedule. They satisfied the geopolitical mandates. But spaceflight does not grade on a curve. Atmospheric re-entry does not respect a spreadsheet. Let's be precise about what this means. When the Orion spacecraft hits the invisible boundary of the Earth's exosphere at 24,500 miles per hour, every single piece of human rationale will instantly burn away. The compromises will evaporate, the probabilistic risk assessments will become entirely irrelevant. The only thing left in the universe will be the brutal, uncompromising laws of thermodynamics and fluid dynamics. The 5,000-degree bow shock will form. The plasma will encase the vehicle, the acoustic trauma will violently shake the titanium skeleton, and the solid blocks of Avcoat will begin to cook. Think of it like watching a fuse burn toward a known explosive. The thermal energy from the plasma will ruthlessly radiate deep into the 3-inch thickness of the heat shield. The chemical resins will undergo pyrolysis. The hydrocarbon gases will aggressively expand. And because NASA refused to halt the assembly line to install a breathable honeycomb matrix, those trapped gases will furiously fight against the unyielding, uncharred outer shell of the blocks. The spacecraft is hurtling toward the exact physical trigger that caused its predecessor to violently fragment. This is the point of no return. We are not waiting on a simulation. We are waiting on a collision. When Weissman, Glover, Koch, and Hansen plunge into the atmosphere on that newly modified, heavily steepened trajectory, they will be subjected to an aerodynamic braking maneuver fundamentally more violent than the one originally designed to keep them comfortable. The G-forces will crush into their chests. The physical toll on their bodies will be immense. But the true, terrifying variable is happening mere inches beneath their seats, completely outside of their control. If the steep trajectory works, the intense heat will flash-bake the Avcoat before the internal gases can catastrophically pressurize. The shield will sweat, the boundary layer will hold, the vehicle will survive. But if the math was wrong, if the chaotic multiphysics of a 5,000-degree thermal shockwave refused to conform to a simplified lumped parameter model, the gas will pool. The pressure will overwhelm the tensile strength of the solid resin. The material will detonate from the inside out. Heavy, jagged chunks of the primary thermal protection system will be violently ejected into the Mach 32 slipstream. The plasma will flow into the newly formed craters. It will seek the recessed separation bolts. It will hunt for the titanium orthogrid. The margin of their survival will be dictated entirely by the depth of a random, unpredicted structural failure. Stay with me for a moment. Let this final truth land. The United States space program has knowingly strapped 4 of its most capable human beings into a vehicle possessing a recognized, unretired structural flaw. They are relying on a procedural software fix to outrun a physical-chemical detonation. They are flying a heat shield design that the agency explicitly abandoned for the very next mission. They prioritized a geopolitical launch schedule over the absolute, deterministic certainty of materials science. The press conferences are finished, the rhetoric is exhausted, the mathematical gambles have all been placed. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen are falling toward the fire. The math is done. The physics are waiting.